My dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 616. In this lecture, we will try to understand AlexNet. Our next model is called the AlexNet. It is named after the first author of this research paper. This research paper is ImageNet Classification with Deep Convolutional Neural Networks. Yes, who is the first author? Alex, isn't it? Alex K. After his name, this particular, I can say it is named, AlexNet is named after the first author of this particular research paper. This is a simplified version of AlexNet, which is easier to understand. I will also refer to you actual research paper here. This is the actual research paper. First author is Alex Krejewski and Ilya George Jeffrey E. Hinton. I think you can recall about Jeffrey Hinton. He gave rebirth to the whole of I can say he gave rebirth to the whole of the deep learning. Just see all these authors, Alex, Geoffrey Hinton, Ilya, all of them worked in Google. They left the Google, isn't it? He is the person, Geoffrey Hinton is actually gave rebirth to the whole of the deep, I can say he gave the rebirth to whole of the deep learning. Actually, we discussed about him in our previous lectures also, isn't it? This is a very nice paper in 2012. This was the actual model. AlexNet was the model which was in 2012. It was applied on ImageNet dataset that we discussed one of the previous video. Just try to recall. I already discussed about ImageNet dataset, and this is literally created a big wave of research and funding and developments in deep learning, because AlexNet, I can say AlexNet broke all the records of the pre-existing non-deep learning based techniques, and it showed how powerful deep learning could be, especially for the given problem of object recognition. It is very hard problem actually. So this paper is actually fairly easy for you to read, but I go through the key important and most important points before we go into this paper itself. Let's understand the architecture quickly. This is the architecture. Just try to recall, this is the architecture. So you are given an input image. Let me say you are given an input image which is of 224 pixels by 224 pixels by 3 channels. What are the channels here? You have red, blue, green channels, isn't it? Just say I'm writing RGB. R means red channel, G means green channel, B means blue channel. I request all of you, before understanding this lecture, please try to understand lectures on pooling, padding. Without those background, it may be a little bit difficult to understand this particular lecture. This is your input image. The first operation that I will perform is, what is my first operation? These are the 3 channels. What are the 3 channels? RGB, isn't it? The first operation that I will perform is convolution operation with the stride size equal to 4. Let me say my convolutional operation with the stride size equal 4, and we have kernels of size. What is my kernel size? 11 by 11. There are 96, I can say there are 96 such kernels. This results in, basically, if you apply the stride and convolution, everything, you will get, what image will you get? You will get 55 into 55 into 96 sized images. I will get 96 of them because we have 96 kernels. That's important. So you will get a 3D tensor here, which is of, what is this? This is basically, it's a 3D tensor here, which is of size 55 into 55 into 96. Depth is, what is the depth? What is, which is of depth is 96. This is I have length 55, breadth 55, and the depth I can say 96. You can think of this as a 3D tensor which has length of 55, width of 55, depth of 96, length of width of 55, length of 55, and depth of, I can say, 96. Or in other words, you can think of this having 96 channels, just like we have this. Actually, just we were saying that here you have 3 channels, isn't it? This is channel 1, this is channel 2, this is channel 3. Here you have, here in this case, in this particular case, just like here you have 3 channels. How many channels here you have? You have 3 channels here, isn't it? In similar manner, how many channels here you have? You have 96 channels. That's what it says, isn't it? You can think of this how this have 96 channels. So the first layer is, what is the first layer? First layer is convolution. My first layer is convolution, and the second layer is, what is my second layer? Second layer is max pooling. That's important, isn't it? Actually, what I'm doing, I'm performing max pooling of pool size 3 by 3 with a max pooling kernel of 3 by 3 with the stride of, what is my stride? S equal to 2. So this results in an image of 27 by 27 by 96. What is this 96? 96 channels. What is this? 27 length, 27 width. So what we have done, 27 length, 27 width, 96 channels, isn't it? So what we have done, one convolution followed by one max pooling. First, what we did, first we performed convolution. Then what we did, second one is max pooling. Actually, I can say convolution, and first layer is convolution, second layer is max pooling. I can treat these two things as step 1. The second step that we will do is, in step 2 we will again perform convolution with the padding equal to same, isn't it? Padding equal same. This ensures that what is padding equal same? This ensures that the input size 27 by 27, the input size 27 by 27, and output size is 27 by 27. That's what the padding equal to same, isn't it? That's what padding equal to same will achieve. We have 5 by 5. What you have here? You have 5 by 5 kernels. 256 such kernels. We have 5 by 5 kernels, 256 such kernels, isn't it? So we are getting 3D tensor now. That's important. 27 by 27 with 256 channels or depth of 256. Again, we are performing, again what you are doing, we are getting this, we are generating 3D tensor, isn't it? That's what it says. We are getting 3D tensor now. What is that 3D tensor? 27 by 27 with the 256 channels or depth of 256. That's important. Again, we are performing, actually what we are doing here, again we are actually that just see 27 length, 27 width, and 256 depth, isn't it? Actually just see, again we are performing max pooling, isn't it? Look at this. Initially we used kernel size or filter size of 11 by 11. Then we are using kernel size of 5 by 5. Just see, again we are performing max pooling. What is this max pooling? Max pooling 3 by 3, isn't it? And a stride length of 2. What is my stride length? S equal to 2. And this creates a matrix of size. What is size of that matrix? 13 by 13 into 256. To understand all these numbers, I request all of you to refer my previous lectures where I discussed about striding, pooling, all these things, convolution, isn't it? Again I perform convolution, and again I perform convolution, again I will perform convolution. I have 3 by 3 convolution with padding is same, isn't it? That's important. That's why you have 13 by 13. You have why? That's why you have 13 by 13. Same 13 by 13. You have this 13 by 13 appearing thrice, 3 times. That's because you are using same padding equal to same, isn't it? We are changing number of kernels. Just see, we are changing number of kernels or filters. So eventually you reach 13 by 13 into 256. That's important. Then we apply max pooling. Again, what you are doing here, again we are applying max pooling with stride length of 2. What is my stride length of 2 and 3? What is my filter size? My filter size is 3 by 3. Max pool filter eventually isn't it? Eventually you reach what you are reaching 6 into 6 into 256. This is I can say these cuboid shapes, I can say these are cuboid shapes, isn't it? These cuboid shapes are very interesting. Now look at this length of 6. What is this length? Length of 6, I can say width of 6 and depth of 256. Then we apply flatten operation. Just try to recall, we already discussed in MNIST data set also flatten operation. That is, what is this 6 into 6 into 256? That is essentially 29216. I have two fully connected, I can say two fully connected layers. My final layer, which is softmax layer, isn't it? My final layer means what? This one is my final layer. Just see this one. This is my final layer. This is my softmax layer. Just try to understand this part. This is my softmax layer, isn't it? This is my softmax. This is my final layer, which is softmax layer, isn't it? What was this network? What was this network was trying to achieve? Just try to recall. It is trying to solve ImageNet problem. This is, I can say, 1000 class classification problem. What type of problem it is? Just the output is 1000 classes. I can say this is 1000 class classification problem. Now couple of things that you should note. Kernel size is here. What is my kernel size here? It's 11. Initially kernel size is 11 by 11. Just see what is my kernel size. It's 11 by 11, isn't it? Just try to recall what you did here. Now let me repeat. Now a couple of things that you should note. Kernel size here is, what is this kernel size? 11 by 11, and again you have kernel size 5 by 5. Again you have kernel size 3 by 3. Remember, this is one of the successful model as of 2012. Lot of things changed since then. We will see far more complex models in some of the future videos. Alex and his team designed this network after lots of experiments. Since we understood the architecture, we go back to the research paper in my next lecture. I request all of you, before understanding this particular lecture, please go through my lectures which I recorded on padding, max pooling, convolution, strides, all these things, so that it will be easier for you. If you have any difficulty, please keep a comment. Thank you very much.